Докторка астрофізики, науковиця в Інституті астрофізики Андалусії, це Іспанія, та доценту в Інституті космічних наук і геопросторових досліджень Ефіопії. Досліджує формування та еволюцію галактик. Міряна – почесна лекторка в Університеті науки і технологій Мбарара в Уганді. І ось зараз під ваші оплески запрошуємо Mirjana Povic. Ваші оплески! Пані Mirjana. Так, а можна одну секунду? Так.
Yes. Okay.
Yes.
Thank
Welcome.
you very much. Yes. Good evening, everyone. It's really a pleasure to be here. I'm very grateful to organizers for making this conference. I'm really impressed with the amplitude and the level of the organization, and then having people here even at this hour. So my huge thanks once again. So this talk, as you can see, will be about galaxies. So we are shifting a bit the topic. Actually, how do I go to the next slides?
One moment.
Okay, yes. Yep. Okay, great. Sorry, where is the, this one, no? To go back? This one, okay, perfect. Okay, perfect, that works perfect. So as I said, this talk will be about galaxies. So my field of research is extragalactic astronomy. And we will start a bit with this part that is just summarizing a little bit for those of you who are not familiar with astronomy. So it's a science that we explore the universe as a whole. And here you can see a bit the summary of the components and at the same time different fields in astronomy that we are having and studying. So starting from our Earth, the solar system, where we have the planetary sciences. When we go out of the solar system, we will find ourselves with other stars that are there, the stellar astronomy that is studying the properties of the stars, how they form, how they evolve. Then we have the Milky Way that is our home, and galactic astronomy that is focused on understanding the structure of Milky Way, kinematics, dynamics of the Milky Way, its evolution, history. And then when we go out of the Milky Way, we find ourselves with many other galaxies. So currently, with the telescopes that we have on the ground in the space, we managed to observe already several millions of galaxies. But we know through simulations, we expect that there are 2 to 3 trillions of galaxies that could be there in the universe. So my field of research is related with the galaxies and studying the properties of galaxies. In particular, their structure, their chemical composition, but also their nuclear activity. And that will be the topic that I will go through now. So we will first introduce ourselves with what active galaxies are and what are, okay, there are parts that are missing here. So the active galaxies are galaxies that host in their center what we call active galactic nuclei, or AGN. So all this talk will be about AGN and active galaxies. So the AGN is the very compact region in the central part of the galaxy. And that's the region from where we are getting huge amounts of energy across the whole electromagnetic spectrum. So when you go from very high energies like gamma rays, X-rays, to very low energies like in radio waves. So here you can see 2 examples of 2 different active galaxies. Some of active galaxies have these relativistic jets, and these relativistic jets are the materials, it's a material that is moving with relativistic velocities due to the very strong magnetic field, and they are very particular features, because you can see here in the center is what is the galaxy itself, similar to what would be our Milky Way galaxy. But you can see that these jets can take the size that is several times the size of the galaxy itself. which means that we are talking about very, very particular, very powerful events and processes, mechanisms. But not all active galaxies do have these relativistic jets, and I will mention about that a little bit after. Okay, so this is coming later. Okay, great. So why active galaxies are really amazing sources? Because they are some of the most luminous sources that we have in the universe. And what that means, here you can see the comparison in the luminosity. For just galaxies that are normal galaxies, like our Milky Way, the luminosity, so the brightness that the galaxies, the energy that the galaxies are emitting, that are normal galaxies, will be due to the light that is generated by all the stars that are in the galaxy. However, when you come to the active galaxies, you will have the light generated by all the stars, but then in addition, the light coming from this active galactic nuclei that is in the center. And you can see that this luminosity can be 10,000 times higher than what is the light emitted by all the stars in the galaxy. So we are again talking about a very, very particular mechanism. So if we would compare, you can imagine that in our Milky Way that has between 200 to 400 billion stars, some of them similar to our sun, others with smaller mass or more massive. So when you have the active galaxy, whose the AGN, so the size from where the light will be emitted, can be compared with the size of the solar system. However, you can get, as I said previously, tens of thousands of times larger energies. So basically, you can see here the comparison of the solar system size in comparison to the Milky Way size, and then how many more times we are getting larger energy. So that would be a bit like if we compare the size of the Milky Way with the size of the US, then the size of the AGN would be the size of the grain of sand. However, you will be getting these huge amounts of energy. And if we compare with something that is the most catastrophic that we know on the Earth in terms of the energy, such as the atomic bomb, then one AGN would emit around 10 to 27 times more, so it will be 10 to 27 atomic bombs per second, what is the energy of the AGN. So once again, we are talking about very, very particular events that are happening in the universe. And for a long time, it was a big question how this energy is really generated and how galaxies are able to emit so much light. So before answering that question, I will just mention the importance of studying active galaxies. So because they are the most luminous sources that we have in the universe, they're basically our cosmological labs. So what do we mean by that? We mean that they are the most distant sources that we are able to observe with our telescopes. Because all telescopes that we use, even the best telescopes that we have on the ground and in space, they all have their limitations. So larger the telescope, fainter and fainter sources we can observe, but then we always come to the limit, to the limiting capacity of every telescope. So that means that the galaxies that are the most distant from us will be actually, that we were able to observe, are actually active galaxies. So we can use these galaxies to understand their properties when the universe was very young, up to nowadays, and then study the evolution of galaxies, but then universe as a whole as well. And that is saying that I will now mention, so I don't know why it's not changing. Okay, so I will now mention what is the energy source. So basically now we know that the energy source of these AGN are supermassive black holes that are in the center. We know that almost basically all galaxies do have supermassive black holes in their center, but it doesn't mean that all galaxies are active galaxies. But those galaxies that have very massive supermassive black holes, above 10 to the 6 solar masses, they can get into this AGN activity. So basically, the mechanism that is responsible for emitting these huge energies, is the accretion of the material onto the supermassive black hole. So similar as you can see here. So all the gas, dust, all the material that is attracted by the gravitational force of the supermassive black hole, that, as I said, can be 10 to the 6 and above solar masses, will be accreted onto the supermassive black hole, and due to that accretion, you will get the liberation of huge amounts of gravitational energy that then we can detect at all parts of the electromagnetic spectrum. And there are different observational evidences that the supermassive black hole do exist. Until a few years ago, until 2019, most of the evidences, observational evidences, were also indirect. But since 2019, we were able for the very first time to observe using radio telescopes, the system of radio telescopes in this project, Even Horizon Telescope. So for the first time, we were able to observe the supermassive black hole in the center of M87 galaxy, and then the supermassive black hole in the center of our own Milky Way. So this was the huge step in the history of astronomy, that for the first time we are able to actually observe the black holes, the supermassive black holes, knowing that that they are very, very compact in the centers of galaxies, being obscured by all the dust, the gas, stellar component that is there. So this was really one of the revolutionary findings. And now I will, sorry, I don't know why is this, it's like this. So there are, okay, so this is the slide. So I will just very briefly introduce that this AGN, now we know what is their model as well. So they have very, very particular physics and very complex physics. I will not go into the details of all components. You can see that, so this is a bit the model that we have in the center of each galaxy, this supermassive black hole, the accretion disk that is accreting material, then this torus that is made mainly of dust and gas, and then around that you can have gas, the gas that is very hot and that can have different densities, temperatures, and so on. And in some cases you can have these relativistic jets that we already saw previously. So observing and analyzing these sources is not easy at all. And I will mention just in a bit why they are not easy to be studied, but they really, being so complex, they really have complex physics, because you will need, as I will mention later, the data across all electromagnetic spectrum from high energies to low energies, because, for example, to get information from the accretion disk, you need ultraviolet data, ultraviolet telescope. This obscuring torus will be emitting in infrared. The gas that is around supermassive black hole and the accretion disk will be emitting in optical. And then these relativistic jets are observed in radio. So you need to develop the telescopes and instruments across the whole electromagnetic spectrum in order to really understand their full physics. But then in addition to that, you go from classical Newtonian physics to relativistic physics as you are approaching the supermassive black hole. So very, very complex physics, which is really bringing us to the border of our knowledge. They can live in different types of galaxies that are having different morphologies, which means that they can be really very, very diverse. And then also, they live in different environments, and they also can have different properties. So here I will not go into the details, but you can see here the spectra. So basically how the intensity of the light of these galaxies is changing with the wavelengths, and you can see these peaks in the intensity. These peaks in the intensity at particular wavelengths are actually telling us what is the real physics behind. what is the chemical composition of these galaxies, what is their temperature, what are their velocities of the gas around, and we can then study plenty of other properties like the mass of the supermassive black hole, the luminosity, and so on. So this kind of data we get in spectroscopy, and this is one of the part of my research that we are really passionate about. But as I mentioned, you get like all different type of spectra, which means that there is a huge diversity of these sources. And this is one example of what I said, that we need multi-wavelength data. So these active galaxies are really bright across the whole electromagnetic spectrum. So now pay attention here. This is here you can see the data of Centaurus A galaxy, that is the closest active galaxy to us. And you can see how this galaxy looks like if you use X-ray telescope that you have to have in space, because the X-rays cannot go through our atmosphere, so you cannot get X-ray images of galaxies from the ground. So you need a space-based X-ray telescope, and this is how this Centaurus A galaxy looks like. So this is in high energy, so we are talking here already about billions of kelvins in temperature. So you go here from billions of kelvins to only few kelvins in radio regime. So you can see how this galaxy looks like in X-rays at billions of kelvins temperature, in ultraviolet, in optical, and then infrared, and finally in radio. Going once again from high energies, tens of billions of kelvins, up to the radio, where you are mapping the cool areas, the coolest areas of the galaxy. And this is how then the galaxy would look like when you now combine all the components. So what you can see here is that basically, if you want to study the stellar component in this active galaxy, so what are the types of the stars, their chemical composition, and so on, in the X-rays it will be almost impossible, because you can only see the emission from the most massive galaxies, most massive stars, and the stellar remnants like supernova explosions and so on. So to study the stellar component, you need optical and ultraviolet. In order to study the dust in these galaxies, you have to go to infrared. In order to study the property from the central part of the galaxy, the AGN itself, you need X-rays. And to get information about these relativistic jets, you will not get that in any of these images, but you have to go to the radio telescopes. So this means that, once again, that through these multi-wavelength studies, we can actually study the physics of AGN. So in that aspect, it's hard because we need a lot of data, but at the same time, we can use this for really improve the technologies and our understanding of physics across the whole electromagnetic spectrum. This is another example. So this is the part of the sky observed in optical, and now pay attention to this galaxy here. This is a massive giant optical galaxy, massive giant elliptical galaxy observed in optical. So this image has been taken with optical telescopes. So you can see many galaxies that are there. Now pay attention how the same part of the sky looks like when you use radio telescope. The interferometer, the radio telescope that is called Mirkat, that is made of 64 dishes. So you will get something like this. So it's really impressive. So this is in optical. The active galaxy, you can see all the stars that are there. When you now go to the radio, you don't see any stellar component there, but you will see these massive radio jets with all these lobes that are interacting with the surrounding. So very, very impressive sources, and also the data that now we are having. And now you remember what I said, that these galaxies are our cosmological labs. So here we can see the two most distant galaxies that have been observed up to now. So the two most distant galaxies and the oldest galaxies that, as a humanity, we managed to observe, and that's thanks to the James Webb Space Telescope that was launched a few years ago, and that is currently the best facility that we have. So these are the two quasars. These two quasars emitted light when the universe was only about 300 million years old. And both of them are active galaxies. They are AGN. They are some of the quasars are some of the brightest AGN. And now these galaxies, so observing these galaxies that are so massive, when we already have these supermassive black holes that are very massive when the universe was so young, it is now putting under the question all our models of galaxy formation and evolution. So we are getting to very, very interesting times. So what we are trying to understand is actually how the evolution goes. So how the properties of these active galaxies change across the cosmic time, because we know that all the properties of the galaxies, here you can see in terms of the morphology, that the galaxies nowadays we can see with clear structure, with spiral arms, being elliptical, spiral, irregular, but we know that when the universe was younger, the galaxies had very, very different, they were more diffuse, they had very different properties. And very similar is in terms of the nuclear activity. So why should we care about AGN? This is a bit the summary. Well, first, because they really have very particular, very complex physics, so they make a challenge, they are a challenge for us, bringing us constantly to the border of our, let's say, knowledge, and that push us to develop more and more sensitive telescopes, instruments across all the electromagnetic wavelength. They also are, as you could see, high energetic sources. So that means that we can, through them and their research, work on the development of high energy physics that has very strong application in agriculture, medicine, and so on, like all the X-ray diagnoses, the gamma ray diagnoses, and so on. They are also the most probable sources of the origin of cosmic rays. And cosmic rays have a lot of impact for the space weather and all space technology and satellites as well. And then, as I said, they are really fundamental for understanding the evolution of the universe in general. So these are some of the examples. This is the project. I think I'm running out of time, so I will not speak much, but this is one of the projects that we are starting now. So for the past 20 years, I spent quite basically half of that time working full-time in Ethiopia, South Africa, collaborating with many African countries. And I just wanted to mention this project that we are now starting. It's a project where we are doing very particular observational technique, where we are getting these spectra across the galaxy using one of the new instruments built in South Africa. And it's a project that it will be, by the end of the term, in the next few years, the biggest, it will bring the biggest sample with this new type of data. I would like to mention this because through this project the aim is not only to study AGN, but also to make the science more diverse and more inclusive. So you can see that there are 14 African countries that are participating, more than 80 members that are there. And here are the students. So this is another example how through the fundamental research in galaxies, galaxy formation, evolution, we can actually again contribute to the development of education, development of science, improving the education at a higher level at the universities. And you can see here our students, some of the first students that together with my colleagues from different African countries, so mainly from Ethiopia, because that's where I worked for the last 10 years, but then other African countries as well. So the very first students that did their master, their PhD in astronomy, and I have to say all of those who finished their master, they continue their PhD in astronomy, getting competitive scholarships across the world. Those who finished their PhD, they continued working in Africa at different universities and research centers. So this is again the example that even by doing the fundamental research, studying the universe, space, we can actually, through the human capacity development, building, improve the work on social economical development, and all these aspects. No? So through these people that really are the future, we can work on human capacity building, education development, bringing for the first time the science in astronomy, in space, in different African countries, giving more visibility to the science done in Africa, Africa, because we also have great science there, and not only the problems, difficulties, improve the international collaborations, and then very important, inspire next generation of scientists across Africa and across the world as well by making the science more diverse. And here you can see, this is the last slide, so you can see a bit what is the current status of astronomy in Africa. In this map, these are all current infrastructure developments, so either the observatories that are already there or the observatories that are under the development. Here you can see all countries that are having some development in professional astronomy, either on institutional development, postgraduate programs, and so on. And here you can see on the bottom the amateur astronomical societies, which is also showing how much the interest in astronomy science is really growing across the continent. And that is all. Thank you very much, and my best wishes for everything. Yes.
Дякуємо вам, дякуємо. Так, ну що, у нас є ще час у нас на запитання? От одне запитання. О, це я знаю. One question. Будь ласка, піднята рука, якщо хто не розуміє, put your hand up. Ні? Все зрозуміло? Точно? Бо англійською було. Є, будь ласка. Людина навіть встала, щоб я побачив вашу руку. Будь ласка.
Thank you for your presentation. I came to the end of it. Unfortunately, I was in the other room. Can't have enough time for everything. This is a very interesting topic about astronomy. I would like to ask you, what are some, let's say, major problems that we have nowadays? What are we limited by? What will we have in the future if some certain problems will be solved? Maybe the technical ones, maybe some kind of, that we don't have enough scientists, perhaps.
Oh, Sorry, I didn't, because of the sound, I didn't really understand.
What are the major problems in astronomy? What should we deal with in order to progress further?
Okay, so the major open questions, that we currently have, that's the question, no?
Sorry?
The major open questions that we currently have.
Yeah.
Yes.
What do we have to solve?
Yes, actually there are still many of them. So definitely in terms of what I was saying here, for active galaxies, galaxy formation, evolution in general, for active galaxies in particular, there are still many questions that we don't really know. For example, what is the mechanism that brings all the material toward the center and then producing this active phase in the evolution of galaxies? It's still not known. What is the origin of these relativistic jets, how they form? We also don't know. How they really evolve across the cosmic time is still an open question. Then when you extrapolate that to like some of the main questions that we have, I would say that definitely some of the clear picture of galaxy formation evolution is one of the questions, especially now when we focus, because the last 10 billion years in the history of the universe, we already have a lot of data. But the first 3-4 billion years, what really happened in the universe in that time is still very much unknown, because we only have few galaxies that were observed, and they are all these active galaxies. So that is, I would say, with the James Webb Space Telescope and the next generation telescopes, it's something that is really there to be discovered. And what I mentioned, that the two quasars that I shown, the most distant galaxies that have been observed, up to now, the model of galaxy formation that was accepted was that, through observations, was that first in the universe, the small components were made, and then through the merger interaction of these small components, we get more and more massive galaxies. But now having these galaxies that have been observed with these massive supermassive black holes, when the universe only had few 100 million years, the question is, if our hierarchical model still works, no? So confirming these models of galaxy formation evolution is now still under the question. The multi-messenger astronomy is something that is coming for the future. So for example, everything related with gravitational waves, gravitational wave physics, detecting the mergers between the supermassive black holes, and so on, is definitely a field that is coming for the future. And I would say the biggest question that we still have to be answered is really, is there life elsewhere out of our Earth? And that's something that we are a bit, so we still don't have answer on that question because we still don't have capacity to study life outside of the Earth. But now with the James Webb, for the first time, we are able to study the chemical composition in the atmosphere of the planets. So for example, for the first time in the last few years, we were able to detect the molecules like water molecules, methane molecules in the atmosphere of some of the planets. And these molecules, we know, at least on Earth, are very much related with life. So we are definitely entering in the new era and understanding I mean, there are then many other open questions also in stellar astronomy, our Milky Way, and so on. But these, I would say, are some of the main questions that are there. And then definitely, I forgot, definitely the big question of dark energy, dark matter. Dark matter has been there now for a few decades. We still don't really know what is the origin of dark matter. Dark energy, we also don't really understand what dark energy is, how the universe is accelerating and why. So these are some of the components, aspects of the universe and open questions that will still take some time to be answered.
Thank you very much. There are so many unresearched fields. It's just incredible. So many things we have to answer. And I suppose we will be able to, I hope we will be able to do that. Thank you very much for your researches that you came here, that you gave us a presentation. It's wonderful. Thank you very much.
Thank you, thank you.
Дякую вам за запитання. І я хотів би, щоб ми ще раз поаплодували. Thank you.
Thank you.